Welcome to today's lecture. Today we will be discussing output charging and discharging mechanisms in combinational gates in near threshold voltage regime. So, we have discussed a simple and back of the envelope approximate way of calculating logical effort of gates with stacked transistors for inverters and logic part delay in the previous lecture. In this lecture, we will be discussing charging and discharging mechanisms for combinational gates for the output node. This we will use in obtaining more accurate effective current and logical effort models for combinational gates, which we will be using in predicting the impact of variability in near threshold voltage circuits. So, typically we are discussing combinational circuit which can be represented typically by an inverter chain. So, in this inverter chain, when we simulate at any say in 65 nanometer CMOS node. So, these are simulations corresponding to 65 nanometer ST microelectronics CMOS node, planar CMOS node. So, in any such, I mean, it does not depend on PDK, the results are qualitatively valid for any PDK. So, the input would look like this. Suppose typically we are looking at the input and output of this stage 3. So, this is our design under test, device under test. So, what would we observe? The input transition would not be monotonic exactly, and it would have transition of this kind. During the major part of the discharge, the input voltage value is not VDD, it is slightly lesser than VDD in planar technologies. In other FDSY and FinFET technologies, we will observe that it is even more discharging voltage, if you want to call it discharging voltage or switching voltage, that is even smaller than the than 0.795 VDD. It could even be 0.7, 0.8 VDD. Now, this is important because we know that with gate voltage, the currents would exponentially change. So, a little difference in the VDD in gate voltage of the input voltage of an inverter can actually result in a large difference in current and therefore delays. So, where is this input voltage being applied? So, this is V in, this is V out that we are discussing. So, here all the fan out of all the stages have a constant fan out. So, while we have this constant fan out for all the stages, what do we can make an important observation that there would be a one-to-one correspondence between the input and output voltage values. What is the reason for this? So, we have a constant fan out. Suppose the fan out is increased from FO1 to FO3 to FO4. Suppose the fan out is increased from fan out of 3 to 4. So, in that case, what would we observe? Now, fan out is increased throughout logic path, that is the inverter chain, okay, for all the stages. What would it result in? So, since it has been increased for all the stages, would find a similar change in the current drive to capacitance ratio. Capacitance to current drive ratio remains equal for all the stages. What do we mean by this? So, a change in input voltage would result in a certain change in the output current, okay, and a change in input voltage for a stage results in a certain change in the output current, and this would result in a certain change in the output voltage. So, what is that change in the output voltage? That would be C out of the stage into the change in the output voltage should be equal to the time taken, should be equal to the change in the, so the current okay. So, the average current in that small time period into change in time. So, what is that time in which this change in output voltage happens? So, if we see, this would turn out to be, since you are matching the fan out ratio everywhere throughout the inverter chain, we can see that this is, now we can see that the current I out and delta I out is not changing. So, it is increasing by the same ratio. For example, if you are increasing the fan out ratio from fan out 3 to fan out 4. So, in that case, compared to the first stage, the second stage would have an increase in output capacitance of 4 by 3. Likewise, every stage would see an increase in capacitance of 4 by 3, and second stage would also be larger in size by 4 by 3. Therefore, its current would increase by, these currents would increase by 4 by 3 times, whereas the output capacitance would also by the same reason increase by 4 by 3 times. So, what would we observe? That this change in output voltage into C out should be equal to the discharging current, average discharging current in that time into delta t. So, now that average discharging current, if we see, since you have increased the fan out ratio from FO3 to FO4 for all the stages, the average discharging current would increase by 4 by 3 times, because the first stage, whatever it be its size, the second stage its size would increase by 4 by 3 times. So, if you increase the fan out ratio from FO3 to FO4, if this is size C in, then this will increase from 3 C in to 4 C in. So, likewise, this would increase from 9 C in to 16 C in, likewise. So, you would observe that the capacitance also increases by 4 by 3 times for all the stages, the capacitance. So, and current drive, because the size width is increasing, because the width is also increasing. So, this width would increase from 3 W n to 4 W n, if this is having a width W n, size W n. So, what we would see is that the current drive also increases by the, because of this reason, C out increases by 4 by 3 times for all the stages. Okay. And because the current drive is increasing, because width is increasing, the current drive increases by again 4 by 3 times. So, if you work out, you observe that because of the capacitance increasing by the same amount, the current drive increasing by the same amount, you would take the same amount of time for this part of the transition. For this part of the transition, you would take same amount of time, and that is valid for all the parts of transition now. So, therefore, what happens is that you have, whenever the fan out ratio is changing for this design under device under test, you would observe that its input transition time is increasing by 4 by 3 times, and input transition time and output transition time both increase by 4 by 3 times. But going by the same reasoning. So, therefore, we would have a one-to-one correspondence in V in and V out for this inverter chain with exactly matched fan out ratio for all the stages. Now, we also observe some interesting phenomenon which we will discuss. Why is this switching input voltage? If we call this as switching input voltage, why is this coming out to be different from VDD? See, this is also not VDD, this is actually, this voltage is not VDD as we have discussed in the previous lectures. It is actually slightly lesser than VDD, and that is because of the leakage current of the N MOSFET. So, this we should observe as we had discussed in the previous lecture, slightly smaller than VDD because of leakage current of N MOSFET. So, and likewise we also discussed that this would be slightly larger than 0 because of the leakage current of P MOSFET, but this is different and we are calling it switching input voltage. Let us call it switching input voltage. What is the reason for this? So, if we observe the cross sectional diagram of an N MOSFET, the substrate and channel are P type, LDD is N type. So, when the gate voltage is 0, the substrate is depleted or channel is depleted. LDD, because of the work function difference, is either depleted, or as you increase the gate voltage, the LDD would come into depletion region in the channel would increase, and in the LDD you would go towards accumulation. So, once it from depletion, once it goes into accumulation because of this fringing field, you would observe that there is a sudden increase in capacitance, because in accumulation the capacitance is quite large. So, that sudden increase in capacitance causes the transitions not to be monotonic, but because of this coupling capacitance between the input and output of an inverter. So, this would come out as a coupling capacitance between the input and output. So, if we have this as the inverter, you would have a coupling capacitance here. This coupling capacitance is actually coming from the CGD here. So, what would happen, and suddenly, so when it moves from, when the LDD, this we are calling LDD. So, when the LDD Vg, now Vg of this transistor is V in of inverter. When it increases, the LDD N type LDD goes from depletion to accumulation. This causes a sudden increase in the coupling capacitance C, and therefore, you observe. So, since the output is falling, so there is a back coupling from the due to the back coupling from out to in. V in does not increase rapidly, and this is what, therefore, this results in this switching input voltage which is smaller than VDD. So, now after this we will discuss the various components of currents as they which discharge or charge the output node. We had seen till now that there is a one-to-one correspondence in V in and V out values if you maintain the fan out ratio of this inverter chain, or in other words, if you maintain the stage effort of the inverter chain for each stage, then there is a one-to-one correspondence in the values of V in and V out. So, even when you increase the fan out or per stage, suppose you have increased it from fan out 3 to fan out 4 for each stage, then for whatever value of V in, you had a certain value of V out. For when you had a stage ratio of fan out 3, you will have the same value of V out for the same value of V in for when you have a stage ratio of fan out 4. That is what we mean by this one-to-one correspondence between the values of V in and V out. One thing that let us, to put things in context, let us understand how standard cell layout is done. So, these standard cells are used for semi-custom design, as you might be knowing, and they abut with each other. That is, when you place standard cells beside each other, they abut with each other, and their power VDD supply lines and ground VSS lines would merge with each other. So, what happens is, this is one standard cell with VSS here, VDD here, this is another standard cell with VDD here, VSS here. Now, when you bring them together, these VDD and VSS lines would merge with each other, and the output of this and input of this, these two standard cells would abut with each other. For example, if this is the inverter chain that we are discussing and these are the inverter standard cells, then they would abut with each other, okay, and the supply lines would, power supply rails would merge with each other, and each of the standard cell would look like this. Now, because you need to abut and merge these, you need to maintain a certain distance between VDD and VSS that cannot be changed, and this is determined by track height of the standard cell. Track height of the standard cell determines the maximum height that the standard cell can have, and typically it is VDD and VSS lines which are at the edges of the top and bottom edges of the standard cell. But the implication of this is that when you have this fixed track height, you allocate some part of the height for the P well or N well, and the other part for the P well if it is a dual well technology or for the substrate. So, you can have P MOSFETs only in the N well and N MOSFETs here in the substrate. So, you can have a certain height for the P MOSFET. So, if you have wider devices, you go for fingered layout. So, in this is the gate, and all these three gates are parallel, and this is the source, that is diffusion, and these are drain nodes. So, this is also diffusion. Now, this is the width of the finger, and in this example we have 3 gates in parallel. So, width of the device is 3 times width of the finger in this example, and the current is ideally it is 3 times the current of per finger, okay, from source to drain. The current would be flowing from the drain to source, current of each finger. Okay. So, for this finger it would be flowing in this way. Now, these 3 currents would add up at the source and drain, isn't it? So, 3 times the current of each finger would be the current of the device ideally. Why I am saying ideally? Because of narrow width, inverse narrow width effects. So, you would have non-idealities because of non-idealities, narrow width effect, inverse narrow width effect, well proximity effect, mechanical stress. These would all be layout dependent effects. So, there would be all such layout dependent effects, but if we for the present ignore them, then we would say that the current of the device ID is 3 times finger current of each finger. And what about capacitance? Now, there is this. So, if you imagine this in this way, you find that there is a area capacitance associated with the source and drain to body. So, it is, suppose this is drain and this is CDB, drain to body. Okay. Likewise, you have overlap capacitance from the gate to the source or drain, overlap capacitance. Okay. Now, this is because of fringing fields in the spacer. Where is the spacer? This is the spacer that we have drawn. So, you have spacer on both the sides here. So, you have spacer here and spacer here. Okay. Likewise, you have spacer here, here, here and here. Let us specify this. So, if we look at this, we would say that the capacitance CDB and this overlap capacitance and the gate capacitance, all kinds of gate to drain, gate to source, these are all proportional to device width. So, and we call the parasitic capacitance. So, parasitic capacitance is therefore a sum of all these, drain to body, overlap and several other components, and we would see that all of these are proportional to the width of the device. So, parasitic capacitance itself is proportional to the width of the device. This we will keep in mind. So, current is proportional to the number of fingers or total width of the device, or number of fingers, you can also say, or number of fingers. Okay, number of fingers. Current is proportional to this total width of the device and the number of fingers. So, and what about this overlap, this gate to drain capacitance? Where is this gate to drain capacitance? It is the gate to, suppose this is drain. So, gate to drain capacitance, which is overlap capacitance. It could also be because of the channel, but if the device is not in saturation, then it is also because of channel, but if the device is in saturation, it is purely an overlap capacitance, gate to drain. Now, that capacitance is also proportional to width. As you can see here, as the width increases, gate to drain capacitance would proportionally increase. So, this gate to drain capacitance of both the devices. So, this is the input output coupling capacitance. Now, this is also proportional to width, as you can see here, the gate to drain capacitances are proportional to width. So, we keep this in mind. So, in this lecture, we have discussed the inverter charging and discharging mechanism, and we have discussed how in near threshold voltage the charging and discharging happens in near threshold voltage regime, and we have discussed the one-to-one correspondence between input and output of when you maintain the fan out ratio of an inverter chain. We have discussed the levels of the input voltage, which level of input voltage is slightly smaller during the switching than VDD. We have discussed a possible reason for that, and we have discussed the parasitic capacitances and currents of an inverter, and when the inverter is a standard cell. So, we have discussed with respect to width and with respect to number of fingers how the parasitic capacitances and currents would behave. Thank you.